Although the category of nonlinear analysis contains a wide range of different types of analysis, in this webinar we are focusing to the force-controlled nonlinear analysis. Instead of a formal and deep mathematical approach, I would like to give visual explanations of the theoretical background that AxisVM uses for the implementation of the analysis procedure. AxisVM uses the Newton-Raphson iteration method to solve the nonlinear problems. Let's start with its well-known illustration for a single degree of freedom system. The mathematical model of a single degree of freedom nonlinear system is a nonlinear algebraic equation. It describes the force response of the model with respect to any arbitrary displacement. For a mechanical representation, it can be considered as a simplified model of a bolted joint. We would like to find the displacement solution for a given load P with the Newton-Raphson numerical method. This method contains two steps. At first, the load process is divided to load increments. Then, an iteration method tries to find the way from the equilibrium point of the last load level to the next one. The exact solutions at certain load levels are marked by the green circles, while the red circles denote the trial points of the iterations. During an iteration, the nonlinear function is approximated with its tangent. The written equations describes an iteration step. The exact solutions can only be approximated. For the decision whether the trial point may be close enough to the exact solution, the fulfillment of predefined convergence criteria is checked. In single degree of freedom, everything seems to be simple. Let's see the multi-degree of freedom case. A simple solution is to change to vector variables with a system of equations. But in this approach, a four-dimensional diagram would be necessary to visualize the two displacement and the two force components of a two-degree of freedom system. It is impossible to draw. Since I would like to draw anyhow, I will take a workaround. Let's introduce the function of total potential energy. It is a scalar-valued function above the space of the state variables, which are the displacements. This function is connected to the equilibrium equations with an integral differential relationship. In the view of the potential, different function belongs to each load factor, and the solution point of the equilibrium equations at a certain load level is the minimum point of the related potential function. These minimum points are marked with the green circles, while the red circles show the trial points of the iterations. The reason why I introduced the potential function is that it remains scalar valued for multi-degree of freedom systems as well. Therefore, we can visualize the two-degree of freedom case by drawing the potential function with an isosurface view on the plane of the two displacement components. In this view, different map belongs to each load increment, and the solution point of the equilibrium equations is the minimal point of this map. Comparing these maps with the single degree of freedom curve, it can be seen that the iteration procedure in the multi-degree of freedom case is not as simple as in the single degree of freedom case. It seems like a rhapsodic pathfinding procedure on a complex surface rather than a monotonic approximation. Finally, we should imagine it for 10,000 or 100,000 degrees of freedom. Let's get a nearer view of a map. For a large model with a lot of nonlinear elements, the hypersurface of the potential function can have a very complex geometry. In several cases, even more than one stable or unstable solution points may exist. Moreover, the solver cannot see the whole map. It can calculate the force response and the tangent stiffness only at the trial points, and it has to navigate on the basis of this view information. I think this picture is so expressive for why the convergence of a nonlinear analysis is so hard to achieve. Finally, the solver doesn't know whether a trial point is near enough to the exact solution or not. It can only guess based on the fulfillment of some convergence criteria. Let's see these criteria, which are limit relations prescribed for some error values. Look at the last iteration in the second load increment. It is between the light blue and the orange circles. At first, let's see the convergence in displacement. Let the displacement in the last iteration may be denoted by delta U. Moreover, let the total displacement measured from the unloaded case denoted by U. In multi-degree of freedom case, these are vectors having a scalar component for each degree of freedom. The relative error in displacement is defined as the quotient of the norms of these vectors. In words, this error value describes how much the whole structure has moved in the last iteration compared to the total displacement measured from the unloaded state. This type of convergence error can also be visualized both in the state space and on the deformed shape of the model. AxisVM uses the so-called taxicab norm, that is the simple sum of the absolute value of the vector components instead of the length of the vector. At second, let's see the convergence in force. Let delta F denote the difference between the applied load and the force response of the structure at the end of the last iteration. In other words, it is the unequilibrated or residual force. It is the force with which the equilibrium is violated. Moreover, let the applied load at the current load level be denoted by lambda times p. In multi-degree of freedom case, these are also vectors that contains a scalar component for each degree of freedom. The relative error in force is defined as the quotient of the norms of these vectors. In words, this error value describes how much the force equilibrium is violated for the whole structure. In the end, let's see the relative error in work. Its nominator is the work done by the unequilibrated forces on the displacements in the last iteration. Its denominator is the work done by the applied forces on the total displacement measured from the unloaded state. It is a mixed quantity of forces and displacements. When a convergence criterion is fulfilled, it means that the error summarized for the entire model is small enough. For displacement, it means that the whole structure moved small enough in the last iteration. In case of force criterion, the statement is that the sum of the unequilibrated forces for the whole structure is small enough. For work criterion, it means that the work done by the unequilibrated forces on the iterational displacements for the whole structure is small enough. The following question arises: which convergence criterion is recommended to turn on, and in which cases? Displacement criterion is always suggested to turn on because displacements are the primary variables. Its default value is 10 power to minus 3 is tight enough for accurate results. If the convergence is almost but not achieved, it is suggested to loosen the limit to 0.01. It eventuates inaccurate displacements, but we can see an approximate deformed shape that can help to find the reason of the weak convergence. This trick can often be applied for models with reinforced concrete. If accurate internal forces or support reactions are necessary, force criterion is also recommended to turn on with its default value of 10 power to minus 3. This is the case if member design based on internal forces will be performed. If the nodal force equilibrium is violated, tightening the limit to to 10 power to minus 4 or to 10 power to minus 5 is recommended. These settings will be applied in the first case study. Another interesting question arises. What does the fulfillment of convergence criteria mean exactly? The statements belonging to them concern for the whole structure, but their fulfillment says nothing about the distribution and especially about the maximum of the error portions belonging to the individual degrees of freedom. In case of force criterion, it means that although the convergence criterion is fulfilled, the nodal force equilibrium may be highly violated at some individual degrees of freedom. Nodes with stiff supports are the mostly concerned. Its reason is the following. The primary variables are the displacement components. These are calculated directly from the system of equilibrium equations. There is a numerical limit for the accuracy of them. This is small enough to be negligible in the displacement results. But the high stiffness of a rigid support can magnify the small inaccuracy in displacement to a significant inaccuracy in force. Therefore, for nonlinear analysis, the stiffness value of supports considered to rigid would be necessary to decrease from its default value. This problem will also appear in the first case study. Unfortunately, in the present version of AxisVM, the inaccuracy of a support force or moment can only be found in simple cases when the support reaction force components correspond to element internal force components. In complex cases, it is quite a hard work. Therefore, now we suggest ourselves a feature request of some new checking result components. Displacement increments in the last iteration and unequilibrated force components. These would be similar to the existing result components of intensity variation, which are for post-checking of the surface mesh size. Now I would like to speak about the role of increments and iterations. Recalling the picture for the single degree of freedom case, it seems that the increments and iterations play a similar role. It seems that one increment with 500 iterations is more or less the same as 10 increments with 15 iterations. But taking a detailed view, we can see the difference. Its reason is that although both the red and green circles are located on the force response curve of the structure, it only means that the displacements at all of these points are compatible with the support conditions. But the equilibrium equations are fulfilled only at the exact solution points shown by the green circles. It means that the solver has to find a path between the solution points of subsequent increments, going through a series of unreal configurations. Looking at the maps for the multi-degree of freedom case, it can be seen as well. Different map belongs to each load increment. Increasing the load level, the solution point moves far from the origin and the surface becomes more and more complex. Therefore, covering the long and bumpy way to the solution point needs a lot of iterations with weak convergence. Moreover, the convergence can be impossible due to an infinite alternating iteration process. Inserting sub-increments, the solver has to take shorter distances between the subsequent solution points. Starting the iteration process of the actual increment from the solution point of the previous one helps to avoid the hard territories of the map. It provides strong monotonic and fast convergence with a few iterations. We can say that it is usually worse to use more increments because the total number of iterations during the whole calculation can be lower than in case of just a few number of increments. In recent times, we got support models in which the user set only 2 or 4 increments. If the calculation converges well and lots of load cases will be calculated, it is valid to decrease the number of increments below 10. But for troubleshooting any convergence problem, the number of increments has to be set at least 10. If already the starting increment doesn't converge, the simplest way to increase the number of equal increments to 100, 1000 or 10,000 to try out whether the calculation can be kicked off with smaller load steps. If the calculation can start, we can try out a soft starting increment function. It contains just a few starting increments. The few number of them become important when a lot of load combinations have to be analyzed. If the convergence is lost in a middle increment of the calculation, the subdivision of critical increments with the application of an appropriate increment function is necessary. In the following, I'm going to show 2 strategies for that. So, let's see the first strategy on a hypothetical analysis. It can be called the subdivision of all increments after the last converged one. Our plan is to run the calculation with equal increments. This is the red line. The circles show the defined points of the increment function, while the small squares show each of the increments. For better transparency, we applied a division to 4 parts. But in case of a real model, we should use a division to 10. Running the calculation, only the first increment converges. As a next trial, we apply a subdivision for all increments after the last converged one. For that, we define the blue increment function. Running the calculation again, it converges until the third increment having load level 0.375. Therefore, we apply a new subdivision from that load level to all the further increments. Running the calculation again, total convergence is achieved. The arrows between the tables show that for each subdivision, the index of the last increment had to be renumbered and the new point had to be inserted to the increment function. With this simple strategy, the total number of increments increases so fast. Let's see the second strategy that can be called the subdivision of only the non-convergent increment. Our plan is also a calculation with 4 equal increments. Running the calculation, only the first increment converges. Now we subdivide only the unconverged increment and translate the further part of the increment function, leaving the original division on that. The new plan is the blue increment function. Running the calculation again, it converges until the third increment having load level 0.375. Now we subdivide only the non-converged increment again and translate the further part of the increment function, leaving the original division on that. This is the green curve. Running the calculation again, total convergence is achieved. The arrows between the tables show that for each subdivision, the indexes of all increments after the non-converged one had to be renumbered, and 2 new points had to be inserted to the increment function. But with this sophisticated strategy, the total number of increments increases slower than with the preceding strategy. In the end, let's think out what happens if convergence cannot be achieved with successive subdivisions. In this case, the last converged load level tends to a certain value that can be identified as the strength of the structure for the given load situation. While increment function controls the step size of the load increments in the critical phase of the calculation, iteration control influences the size of the displacement increment during one iteration step. There are two types of it. One of them is the automatic constraint for strain increments. It watches the evolution of strain of elements having critical nonlinear characteristics. If the strain state goes through the critical segment of the force deformation curve, the displacement increment in the current iteration is decreased. An example for this case is an element with limit force. Let's assume that the deformation of the element became higher than the limit during the preceding iteration. It is shown by the light blue circle. It causes higher internal force than necessary to the force equilibrium at lambda times p. Therefore, the solver computes a displacement of delta u with the current tangent stiffness to decrease the internal force. It is such long that the state point goes to the other limited segment of the characteristics. In the next iteration, the solver tries to find the force equilibrium again, and the state point goes back to the other limited segment. An infinite loop has been formed, causing a non-converging increment with alternating iteration process. If the option of automatic constraint for strain increments is turned on, the solver recognizes the case when the state point goes through several segments with non-monotonically changing tangent. In this case, the displacement increment is decreased to a constraint value denoted by delta UC. This relocation of the state point helps to find the force equilibrium and to break the infinite loop. This functionality is under construction. We are going to extend it to recognize more complex cases that also can cause the alternation of the iteration process. The other type of iteration control is constraint for displacement increments. This is simply a limit for the largest displacement component. The displacement vector delta u is decreased to delta uc such a way that its largest component to be equal with the limit value. This constraint can break an infinite alternating series of iterations. However, the calculation can take a long time because of the small steps in displacement. It can provide a slow but sure convergence. A practical example for the application of this manual constraint is a simple model with imperfection and only tangent trusses. In the first iteration, both trusses become compressed due to the vertical load. In the real world, an equilibrium state would come into existence with a skew deformation of the structure. But in the solver, excessive deformations occur and the numerical model falls apart because of the loss of stiffness. Turning on the manual constraint, the displacements remain small and the numerical model can also reach the equilibrated state. We often use this functionality for the trial and error procedure applied for support issues. But finding situations when it resolves the convergence problem, the observations will also help to develop the capabilities of the automatic constraint. There are two different types of sources of nonlinearity. One of them is the geometric nonlinearity. It takes into account the large displacement and large rotation of structural elements. The displacements are not simply superposed to the original geometry, but the nodes are really moving during the calculation. Due to deflection, normal forces appear in initially bended structures. The equilibrium equations are written from the deformed geometry, and the displacement of the application point of loads are also considered. However, in AxisVM, the loads do not rotate with the node or element on which they applied. It is called non-failover or conservative load. Any other types of sources of nonlinearity is called to material nonlinearity. One of them is really the nonlinearity of structural elements due to their nonlinear material. But discrete elements with nonlinear behavior also belong to this group. These are, for example, trusses, supports, links, and hinges with only tension or only compression behavior or with limit force. Moreover, springs, supports, links, and hinges with nonlinear or plastic characteristics, and the gap elements as well. For consideration of their nonlinear behavior, the option of material nonlinearity has to be turned on. In this slide, I would like to classify the different kind of nonlinearities according to which phase of the calculation they start to work. Most of them begin to work after a limit of strain or internal force. Yielding of material, cracking of reinforced concrete, truss with limit force, closing of a gap, hinge with slack, or support with backlash are in this group. They are usually modeled with simplified characteristics, of which beginning part is linear. Therefore, in case of these types of nonlinearities, weak convergence is expected only at higher load levels. Only tension or only compression behavior is just a break in the stress strain or force displacement curve at the origin. This switch-like nonlinearity works immediately at the beginning of the load process. Therefore, weak convergence is expected in the first increment. Kicking off the calculation can be difficult. Lots of iterations may be necessary to find the right tension compression configuration of this kind of trusses and supports. Application of soft starting increment function can help to kick off the calculation. Geometric nonlinearity is a continuously working nonlinearity. It can be just a soft nonlinearity if the load level is far from the loss of stability of the structure or of a part of that. However, working together with other nonlinearities, it can cause weak convergence. In such a mixed case, trial calculations with only material and with only geometric nonlinearity can be helpful to find the root cause of weak convergence. It may be only numerical, or maybe the reaching of the limit strengths of the structure. A special source of material nonlinearity is the reinforced concrete model for surface and line elements. The constitutive model implemented into AxisVM for consideration the material nonlinearity of reinforced concrete surfaces, beams and ribs is not a comprehensive material model. It doesn't track the cracking process of concrete and the yielding process of steel during the load history. It is just a simplified model to find the internal forces compatible with the current strains with consideration the nonlinear behavior of concrete and steel. The purpose of this model is only to get a better approximation of deflections by verification in serviceability limit states. Application of this model to track the material nonlinear behavior and to get accurate internal forces by verification in ultimate limit states is not recommended. There are two special properties of the reinforced concrete model that induce two recommended settings of nonlinear calculation parameters. On one hand, since the convergence in force cannot be expected to achieve, only the displacement convergence criterion is recommended to turn on. On the other hand, since the behavior of both concrete and steel material is linear at lower strains, convergence problems are not expected during the beginning increments of the nonlinear calculation. Therefore, the application of the predefined bilinear increment function is recommended for models with only reinforced concrete material nonlinearity. This increment function starts with a load factor 0.4 in the first increment. With this large first step, the whole linear part is computed in one increment, and all other increments can be used to compute the nonlinear part. Further specialty of the reinforced concrete model is the capability for partly nonlinear behavior. In case of epsilon n nonlinearity, only the connection between normal forces and membrane strains is nonlinear. The bending and torsional behavior is linear elastic without any coupling with the membrane behavior. This option is recommended to walls. In case of kappa m nonlinearity, only the bending behavior is nonlinear. But the calculation of the bending moments takes into account the linearly computed normal forces. This option is recommended for slabs. For three-dimensional shell models, the totally nonlinear model is suggested. It is calculated on the basis of a materially nonlinear fiber model with coupled membrane forces and plate moments. For the occurrence of normal force due to deflection, the geometric nonlinearity is also necessary to be turned on. In the last slide, I deal with the runtime error message of singular Jacobian matrix. This topic arose as a question come to the preliminary query of this academy session. The question is, what can be the reason of this error message? The mathematical definition is that the mapping between the parametric and the physical coordinates of the element is not unique. In words, it means that the element is highly distorted. If the error message occurs in the middle of the calculation, the initial geometry of the element was regular, but it had an excessive distortion during the deformation. It can happen only in geometrically nonlinear analysis. It is not simply a large deformation, but a collapse of the element. Its reason can be that the whole structure or a part of that runs out of strength at the certain load level. To find its root cause, the option of store last increment only is recommended to turn off, and the deformed shape is suggested to investigate. If the message occurs immediately in the very first iteration, the initial geometry of the element was already highly distorted. It can be a very sharp element due to any editing mistake. However, if the initial geometry of the element seems to be right, the occurrence of the error message must be a sign of a bug. AxisVM generates a lot of elements in the background for the calculation model. For example, spring elements for nonlinear Winkler or Winkler-Pasternak supports, or rigid elements for the offset of eccentric domains. Any of them might be distorted because of a bug. This is the end of the theoretical presentation. Thank you for your attention. In the following, the academy session is continued with the two case studies. Let's see the troubleshooting procedure on a real support problem sent by a customer. The presentation will show that the process of searching for the root cause of a nonlinear issue is mainly a trial and error procedure. The model is a smaller scaled industrial steel structure with a 5.5 by 12.5 meter inclusion size. It contains two decks in different heights, which are supported by pinned columns and connected to the floor with a ramp or a staircase. The main structure is built up from hot-rolled I and H sections, while the secondary structure uses hollow and L-shaped sections. Modeling-wise, the main structure uses beam elements, while the secondary bracings use linear trusses acting against tension and compression as well. There are three types of supports in the model. The lower deck is supported by fully pinned columns. The ramp has pinned supports with free x-directional setting. and the supports of the columns at the side of the upper deck are pin supports as well, with restricted rotation around the global z-axis. There is a single ULS combination which is relevant for the presentation. It contains the following load cases: 2 permanent load cases for the dead loads of the structure and the equipment, 2 live load cases, one containing distributed surface load on the whole deck and one containing distributed surface load only on the ramp, and finally an equipment load containing nodal gravitational forces acting on the upper deck. First of all, let's check the parameters of the nonlinear calculation and let's reproduce the problem. 4 equal load increments are set with a maximum iteration of 50. Only the displacement convergence criterion is turned on with its default value 10 power to minus 3. There is no nonlinear elements in the model. The source of nonlinearity is only the geometric nonlinearity. Let's start the analysis with these original parameters and let's see the results. We can see the big difference mentioned by the user. The support moment RZZ is more than 100 times higher than the torsional internal moment of Tx of the beam. It highly violates the moment equilibrium. As the first step of troubleshooting, we try to modify only the parameters of the nonlinear calculation. On one hand, it can be the easiest way to resolve the problem. On the other hand, if this trial is successful, the user doesn't have to change the model. At first, let's take a trial with 10 equal increments. It is the default value, and this is the minimum number of increments recommended if any problem occurs. After running the calculation, the value of the beam torsional moment is practically unchanged, and the value of the support moment have decreased to about minus 32 kN to the half of its initial value. It's almost nothing. The problem has remained. Since we need accurate force and moment equilibrium, it is necessary to switch the force convergence criterion on. Let's do it with the default value of 10 power minus 3. After recalculation, we've got a significantly smaller support moment, about minus 0.37 kN, but it is still 10 times higher than the beam torsional moment. Its value hasn't changed. Since we get better results with the force convergence criterion, let's try to tighten the value of that. At first, to 10 power minus 4. Unfortunately, there is no significant change in the value of the support moment. Let's try with 10 power minus 5. With this tightening, the support moment has meant a lot to minus 0.049 kN. Now it is the same order of magnitude than the beam torsional moment, but only the first significant digits are equal. Let's try with a limit value of 10 power minus 6. The calculation doesn't converge. This very tight criterion cannot be fulfilled. It seems that the successive tightening of the force convergence criterion is not the right way to solve this problem. Now, as the second step of troubleshooting, any modification in the model is necessary. Our assumption is that we should modify the support rotational stiffness about the global z-axis. Let's create a new view to display the FZ rotation of the support. Its value is very small. It is about -3 times 10 power -11 radian. This is in the range of the numerical rounding of error. But the high support stiffness of 10 power 10 kN per radian magnifies it to about -0.3 kN. It is in the order of magnitude of the support moment. The first wrong digit of the support moment is the first digit after the decimal point. We are expecting that decreasing the support stiffness with 4 order of magnitude, the first wrong digit will shift 4 times right. Thus, it will shift out from the range of the displayed digits. We are also expecting that parallel with this, the support rotation will also increase with 4 order of magnitude. It will be about 10 power -7 radian. But this value will be still negligible small. Therefore, the softened support will be still able to consider as a rigid support. It will be soft enough to get accurate support moment, but it will also be stiff enough to be considered as a rigid constraint. Let's try it out. As a first trial, let's decrease the rotational stiffness of the support to 10 power 9 kN per radian. The magnitude of the support rotation hasn't changed. It is still in the range of the numerical rounding of error. But the first digit after the decimal point of the support moment has changed to 0, that is equal with the same digit of the beam torsional moment. Let's decrease the rotational stiffness to 10 power 8 kN per radian. Now, 2 digits after the decimal point of the support moment is right. Let's set the rotational stiffness to 10 power 7 kN per radian. Now only the last digit of the support moment is wrong. Finally, let's decrease the rotational stiffness to 10 power 6 kN per radian. Now the support moment is equal with the beam torsional moment for 4 digits after the decimal point. During the process, the support rotation has increased to about -4 times 10 powered -8 radian. It is still negligible as we had expected. As a conclusion, we can suggest to the user the followings. Set the number of increments to 10. Turn on the force criterion with its default value of 10 power -3. Decrease the rotational support stiffness about the z-axis to 10 power 6 kN per radian for all nodal supports. With this modification of the model, the support moments about the z-axis will be accurate enough to fulfill the moment of equilibrium with the needed accuracy. But the behavior of the supports will be still considered too rigid.
The next model today is a reinforced concrete model. This model is not received through a support request, it is actually the slab model from the AXIS-AM step-by-step guide from the website. This model is a roughly 8 by 7 meter wide concrete slab, which has pinned line supports along its 3 sides, and it has 2 nodal supports representing the columns near the unsupported arched edge. Stiffness values for these supports were calculated based on the properties of the walls and columns they are representing. The slab itself is 200 mm thick and it has a material grade of C20 by 25. The model itself has two load combinations defined, one for ultimate limit state and one for serviceability limit state. Both of them contains the self-weight and the two distributed surface load cases, one as a permanent and one as a live load. The problem with the model is the following. While the linear analysis is successfully calculated, running the nonlinear analysis is unsuccessful with its default settings, and it will give the no convergence after nonlinear analysis error message. In most cases, this is the point where we are being contacted for help through the support channel. This type of support requests falls into the modeling type of requests, which means that there are usually no exact solution, or there can be multiple sets of parameters which can lead to a solution. Therefore, investigation is performed on a case-by-case basis, but with using a systematic approach. As said in the previous section, there are usually multiple parameter sets which can lead to the successful convergence of a nonlinear model. Therefore, troubleshooting is in most cases follows a trial and error approach, during which these parameters are being checked. How the steps of this process are applied are collected in the knowledge base as a troubleshooting guide article under the name of No Convergence After Nonlinear Analysis. This article is often referred out to customers as a first step until the investigation is ongoing within our team. The most important points will be presented in this video. First step is to check the reinforcement which is taken into account for the analysis. Convergence of nonlinear analysis of concrete structures is very sensitive to the amount of reinforcement taken into account during the calculation. In this regard, we have three options on the nonlinear analysis tab. To not take into account the reinforcement at all, which is the least favorable option. To take into account the calculated reinforcement values based on a selected load case or load combination. And to take into account the actual reinforcement defined on the structure manually. They should exceed calculated reinforcement values, therefore, by experience, this gives the best results convergence-wise. If actual reinforcement is missing in one of the directions, AxisOM will apply the minimum required amount based on Eurocode regulations in that direction. As the model already has actual reinforcement on the domain, strengthened locally above the columns, let's quickly check how can we make sure if the amount of reinforcement is sufficient in design limit state. Required amount of reinforcement for the selected load case or combination is listed under reinforcement values in X and Y directions, top and bottom positions. Amount of manually added actual reinforcement is listed under actual reinforcement, also in X, Y, top and bottom positions. And the difference of the two under reinforcement difference can be used to check if the actual reinforcement covers the reinforcement needs of the slab. If we see negative values in the color palette, that means that we should add more reinforcement to the slab. Right now in ULS limit state, we need to add more reinforcement both in X and Y directions to the bottom position. Let's raise the amount of actual reinforcement in the two directions by selecting the slab, opening the actual reinforcement editor, and raising the spacing in the bottom X and Y directions. After the application of the changes and going back to the static tab, Nonlinear Analysis dialog, the amount of actual reinforcement will be used in the calculation instead of the calculated reinforcement coming from only the self-weight. In this particular case, this change alone will not help much reaching convergence. So we are continuing with further modifications of the model. One of which is to check the model of nonlinearity under the reinforcement parameters tab. In the model, the kappa m slab option is selected. In this case, nonlinear behavior is considered only in the connection of curvatures and flexural moments. Flexural moments are integrated independently in x and y directions, with the effect of membrane forces on the bending behavior considered. Membrane forces and mxy are calculated elastically. In case of slabs with considerable torsion or complex 3D models in general, nonlinear analysis based only on kappa m bending behavior may underestimate the deflection. Because of this, it is recommended to use the third epsilon n kappa m complex model option. This approach can follow nonlinear behavior related to the 6 strain and internal force components and have better convergence results as well. Let's rerun the analysis with this change applied as well. Calculations still not converge, so we still need to continue with further modifications. Checking if the tensile strength of concrete is taken into consideration during the analysis, we see that the option is turned off. Leaving this checkbox turned off means that the concrete is immediately starting from a cracked state. In this case, concrete zones under tension are not taken into account, therefore the inertia of the cross-section and the overall stiffness of the slab is much lower. Reinforcement in the tension zones are still considered, of course. Which fibers of the concrete cross-sections are in tension is decided upon the first iteration during the analysis. In general, this checkbox is always advised to be turned on. One scenario when it could be considered turning off, when checking an existing structure where we assume that the cracks are already formed and the goal is to determine the final deflection of the structure. Let's rerun the nonlinear analysis with this modification applied on top of epsilon n kappa m nonlinearity option and the consideration of actual reinforcement. In the 10th load increment, the model finally reaches the convergence criteria. In summary, we took the following steps to reach convergence on this particular model. The main conclusions are that the purpose of the nonlinear concrete analysis is the better approximation of deflections, therefore it is only advised to use on SLS load levels. The analysis is sensitive to the amount of reinforcement in the structure. Checking the amount of actual reinforcement is advised. Neglection of concrete tensile strength greatly reduces the overall stiffness of the structure, leading to poor convergence results. And on complex 3D models, the epsilon n kappa m nonlinearity is preferred, as it better estimates the deflections and can have better convergence results as well.